Cool. Okay, so it's been a while since the last open neuromorphic talk, now that everyone's getting destroyed with full-time jobs, startups, and just endless work. But thankfully, Brian reached out to us with his new baby, Project Phasor, and this is a great excuse to get back into it. So just a bit of a background that I don't think is really needed because Brian will go into it in more detail, but where we're going to be looking at how to prioritize the issues in neuromorphic and NeuroAI that are best solved together, with a focus on neuromorphic virtual machines and a shared production quality compiler. A reminder that this is recorded, and so you'll be able to refer back to it once the recording has been posted online. And for all the viewers in the group, feel free to post any Q&A in the chat. A lot of this is going to be discussion oriented, so I will moderate whatever that's going on there. So without further ado, Brian, take it away.
So here's a quick list of speakers for reference. So the main goal of Project Phasor is to address a number of gaps and inefficiencies that's apparent in the neuromorphic ecosystem. One of the main ones is that the existing players are focused on productizing inference at the edge. And it seems like there's a lot that could be done to support training large-scale models. And then NeuroAI is a growing field that I feel we could collaborate more with, help guide them towards more compute-focused workloads. The third one is that building compilers is hard, and I've heard that a lot of people have had issues building compilers for their hardware. And then the long tail of applications makes that even worse. Architecture search within the neuromorphic hardware realm is difficult. You kind of need the help of hardware experts. And data center scale takes a lot of engineering. And in the conventional ML world, there's so many engineers making pod scale, data center scale work, recovering from errors at every single level. And maybe there's a chance to piggyback off of that work that's there already. And I think we need to accept that the future of compute is going to be heterogeneous. One size will not fit all. Neuromorphic hardware will have its space, but GPUs and CPUs are going to be good at what they're good at. And I get the sense that researchers in the field could use more funding for promising research to keep that pipeline full. So the proposed efforts of Project Phasor include neuromorphic virtual machines, neuromorphic compiler, focused on heterogeneous integration with the other compute we'd have to work with, data center scale training, and a joint research fund. Explicitly, this is not going to include a high-level framework. It's more of a lower-level framework to enable higher-level frameworks. So enable people to be creative with how they define their networks and things like that. And then finally, I think the goal should be to do everything in open governance, where it's not biased towards any one hardware vendor, but at least has a process for ironing out differences and So the guiding principles, I think, should be a user-first mentality. I feel like people and researchers have had such a hard time dealing with specific neuromorphic hardware architectures and platforms. And if we could support what the users want first, enable them to move fast, I think that'll be great. Also, we should take a compiler-first mentality. This is something that Grok did after they left Google. They originally did an FPGA-based hardware system, and they could not write a compiler for it. They couldn't do anything other than ResNet 50, pretty much. And this is a story that happens over and over. And if we can focus on the compiler first, get that right, I feel like the hardware will follow. We want to iterate fast, support open development, not just open source, embrace heterogeneous computing, and I think we'll achieve robustness through adversity. We'll, by supporting a number of frameworks and also a number of different virtual machines, we'll end up with a huge matrix of things to support. But I think out of that will come the correct abstractions if we just get all the people in the same room and hammer that out. So yeah, Dylan, I don't know if you have something to add.
You want me to step in, Brian?
Sure. Yeah. Yeah. Did you have slides you wanted to?
Great. Okay. Hey, everyone. For those of you who don't know me, I'm Dylan Muir. I work for SynSense since pretty early on. It's 2 o'clock in the morning for me here, so in the spirit of the phrase, shoot for the stars, you might hit the moon, I'll aim for clarity and hope that I at least reach coherence. So I was on the streets of San Francisco a couple of months ago. I heard about this new project trying to jumpstart neuromorphic processing, engaging academia and commercial enterprises, which I thought was fantastic. And this is really needed because bridges are sorely needed between commercial and academic neuromorphic efforts. What I mean is that large companies like IBM and Intel have historically been really well engaged and well supported by the academic community, but succeeding inside a very large business like IBM and Intel, getting economic traction requires a huge win for that company. And this is, commercial success has come slowly for neuromorphic processing. So these large companies have tended to slowly drop out of neuromorphics. And we saw it earlier with Qualcomm. IBM's kind of out of the picture. So smaller neuromorphic startups are a bit more dynamic. They're willing to take bets on smaller wins. They're willing to work hard to make tools and fill the gaps between academic work and commercialization. But what I've observed is that the academic community strongly supports the large companies, but less engages with the smaller startups. So for example, True North from IBM still gets cited a decade later, but more recent advances from smaller startups can sometimes be a bit overlooked. And I think there's plenty of ways that the academic community can work more closely with neuromorphic startups, even from inside academia, and really support practical development. And I think Project Phasor covers a bunch of important points that can really speed up the impact of neuromorphic processes, the commercial impact, and help to bridge these gaps. And I think they can do so in various ways. So Brian was talking a little bit about open governments. I think that's important to underlie independence, commercial independence, being cross-platform, something which I think Project Phasor can really hit well in a way which other groups may struggle to. Promoting benchmarks, I'll talk about this for a second, and funding translational research, I think is important as well. So as an independent, non-academic entity, I think Project Phasor can easily work on tools that span different commercial entities and also which are not bound by the needs of academia. So companies, for example, can only justify working on tools that benefit themselves directly. And this is particularly true for kind of cash poor small companies like SynSense. Big things like standards and benchmarks are really time consuming and sort of by definition benefit everybody. And this is a tough sell for a commercial entity. SynSense, we come directly out of the academic world. Many of us are old school, old hand neuromorphs. We try to give back as much as we can. So we make our tools open source. We contribute to benchmark definitions and so on. But this always requires a justification of the costs to do so within the company. Salaries, for example, primarily. And it's not always an easy sell. Or as independent entities like ML Commons, for example, which Brian knows well, can really get around these arguments because they're set up to span multiple commercial entities. Academic research, on the other hand, encourages newness, but not necessarily sustainability, I would say, and certainly not commercial impact. So Project Phasor can implement things and encourage work which would not normally be done inside a research group, but which can also spur on commercialization, I think, of neuromorphics. Brian wants to provide extensible compiler or hardware mapper cross-platform for neuromorphic processes that works, that works as a compiler first, as he was saying. This would be fantastic for the community as long as it consolidates efforts between academia and the commercial world. This is something that individual companies obviously struggle with. Again, we've released our own extensible mapping frameworks as part of Rockpool. This partially inspired the design of Near, which is a cross-platform. But although personally we've applied it to several hardware devices, we haven't been able to justify the effort to extend this tool to non-SynSense devices for obvious reasons. You can imagine this would be hard for me to justify to my CEO why I'm building something for Luigi, right? But cross-platform hardware and standards, interfacing standards, are almost required to be able to build a compiler. And investing in standards is much easier from the standpoint of like a power commercial entity like Project Phasor would be. One of the Project Phasor focuses is heterogeneous compute. Brian mentioned this earlier on. Promoting standards for interfacing between neuromorphic hardware and commodity compute is something that Project Phasor is particularly well suited to do. And I think Florence is going to talk about that later on. So let me talk just a moment about commercial success for neuromorphics. The biggest competitor for commercial neuromorphic companies is not other neuromorphic companies, it's commodity compute. So for example, ARM MCUs, low power CPUs, or big compute GPUs, NVIDIA, etc. So one effective way to show the benefits of neuromorphic compute is by implementing benchmarks where there are direct comparisons with commodity compute, and promoting industry benchmarks that can show off the benefits of neuromorphic processes. There's been some movement in this direction for the last couple of years. NeuroBench, for example, there's been a few benchmarking pushes, but the academic community can really support this by using industry relevant benchmarks rather than more strictly academic benchmarks, which obviously promotes more commercial relevance for academic world, helps promote the field more widely outside the academic community, outside the neuromorphic community. But Project Phasor can directly help this by perhaps integrating with ML Commons. There's already some deep connections with ML Commons, and pushing from both ends actually to both include neuromorphic friendly benchmarks in industry benchmarks and to push implementation of commercial benchmarks on neuromorphic hardware. I think Project Phasor can do both of those things. And one way they could do so is through microfunding. There have been a couple of brief discussions in this direction. So the end goal for Project Phasor, if I understand Brian's vision, is to enable funding academic research, which is a fantastic idea, filling the gaps when either commercial or government-sponsored research funding is falling down. But I would suggest that initially, small project awards could be made to enable researchers to translate some of their academic work in the direction of commercialization. For example, implementing commercially relevant benchmarks, rewarding work on commercially relevant tools from inside academia, and promoting bridging these gaps in a way which is more naturally coming from outside academia. but in a way, again, which is independent and not bound to one particular commercial entity. Okay, I think I've taken up enough time here. I'm looking forward to hearing what the others have to say. I don't know how we're doing questions, if there's questions in chat or if you're going to come back at the end.
So no questions in the chat, but to people out there, feel free to leave anything and I'll moderate them. I can come up with something here though. So before we move on to the next speaker, Brian mentioned a compiler first sort of mindset. And Dylan, you've touched on this quite a bit, based on, of course, the work you are doing contributes to what SynSense wants, but that is not at odds with what a lot of other startups or larger scale companies want as well. So given the diversity in neuromorphic architectures, how do we ensure that a neuromorphic compiler remains generalizable yet efficient? And do we want it to be generalizable?
Generalizable to me for a neuromorphic compiler still implies some sort of bias towards neuromorphic hardware, or indeed implementations of neuromorphic virtual machines, which is also going to be discussion on later on. I think having a project sponsored by an independent entity like Project Phasor is really a perfect way to do that, because then you're more likely to be clear of any specific interests and more likely to be able to be generally applicable. Brian, have you got something to say about that?
Yeah, I don't know exactly how things will pan out. Likely they'll end up being some islands that kind of have a stack of their own. But if that ends up happening, there's important glue work to support heterogeneous compute, where if they're different enough, is there a chance for them to work together? That could be something that we tackle.
Cool, thanks. So yeah, thanks Dylan, thanks Brian. Should we move on to Jamie?
Sure, I'm just going to share my own copy of the slides so I can advance them myself. No other reason. But hey everyone, I'm Jamie Knight. I'm a researcher at the University of Sussex, and I'm going to talk to you about open virtual machines for neuromorphic hardware. Sorry, I'm also trying to operate Google Meet at the same time. Yeah, that's not my slides. Give me 1 second, sorry. Okay, I think this is better. Right, so not so good at the Google Meet, it seems. I don't even have Dylan's excuse that it's particularly late in the day for me. But right, so why do we need or want neuromorphic virtual machines? So there's actually, when I started thinking about this, I was talking to Brian, there's actually lots of levels why we want this. So there's a kind of lower barrier for entry for users of neuromorphic hardware. So rather than having to find buy some chip without knowing really what it does and try and map your problem to it, then if you have a virtual machine, then you can at least explore a platform to some degree without having to buy any hardware, which I think would be pretty nice. Like you can run TensorFlow on your CPU if you want to just play with it rather than having to buy anything expensive. But as well as that, I think there's two other kind of uses which I think are really important. So one is for kind of system designers, so to allow the kind of architecture exploration that people are used to in the kind of system on chip development world for neuromorphic. So you can ask questions like, if I add this neuromorphic core to my cell phone system on chip, will it actually help with my workloads? If I run a simulated workload, will it actually be useful to me? And like I've got one neuromorphic core, if I add two more, what would the power implications be? As well as kind of more pragmatically, better debugging. Like Intel's already been name dropped in this, but like one of the things that really annoys me with Loihi is that there's not a good simulator. You make some code that runs in the simulator, or a model that runs in a simulator perfectly well, but that doesn't translate to running on the actual hardware, which is digital. It seems like madness that that's not much easier. So this is not a unique problem to neuromorphic design, I don't think. So almost all modern processors are really system on chips, and what this means is that they consist of lots of cores, often from different vendors, all connected together. So in this random picture from the internet, you've got a GPU core, probably made by one manufacturer. You've got some ARM cores made by ARM. You've got a memory controller. You've got some neural processing units. These are all from different vendors. People who want to make these system on chips, like Samsung, they license these IPs and they jam them together. Like, there's obviously a lot more nuance to this, but this is a basic process. And I think it's important, this is sort of edging into the territory of heterogeneous compute. It's important to allow neuromorphic hardware to be part of this. So what people can add neuromorphic hardware into these systems and see what the benefits would be. And as is with everything, tooling is everything. Like, we need to be using the same tooling as other people. So one possible option here is a thing called System C. As they say in the BBC, other tools are available. System C is pretty simple, which is nice. It's open source. It's just a bunch of C++ and macros that lets you define behavioral models of hardware. They look something like this. So if you're at all used to C++, this doesn't look too alien. It's got some kind of hardware-y classes, but otherwise it's a pretty obvious way of expressing a behavioral model. And there's many extensions to System C. You can do power estimation based on basically how many bits you flip in these inputs and outputs and stuff. And there's even an extension of mixed signal, so you could add analog cores. And more importantly, there's a large library of existing cores, interconnect memory models that you can jam together. And it's useful from Python, which I realize is important in anything adjacent to the machine learning community. So how would we add neuromorphic cores to this library? So there's two kind of levels of model that people care about. There's behavioral models, which are not cycle accurate, but they will give you the same outputs as the real core. And like, honestly, for a typical digital neuromorphic chip, you can probably implement a behavioral model based on publications or documentation, if in the dream world that exists. And also there's some incentive, if this sort of initiative kicks off, that manufacturers would improve the quality of their models so they better match the hardware, because it would be good for their products to have good behavioral models. And also, like, a lot of existing behavioral models used internally will be probably in C++. It seems it's a sensible language to write behavioral models of hardware in. So there's probably existing behavioral models that can be wrapped in System C quite easily. And the other common class of model are these things called cycle accurate models. And again, there's some sort of easy wins here. Like, a lot of open source academic cores, you can already get the Verilog from GitHub, and you can convert Verilog to System C using a thing called Verilator. So we can already start with a nice kind of library of neuromorphic cores, which could really sort of kickstart this initiative and make it useful from the start. So how do I kind of see this virtual machine thing working? So you have this kind of pyramid of stuff, as in everything systems. So maybe Project Phasor could create a library of cores, like models of neuromorphic peripherals, AEI, interconnect, whatever. This would be combined with sort of standard System C core models, interconnect memory, and this could be kind of built into a curated library of reference systems design. So you're going to have a library of one of a SynSense chip, for example, and this would there'll be some standard graph representation. You could talk to this through, and then you can start having something that a compiler can talk to. So this kind of framework would be the sort of thing you'd want to actually build a sort of generic platform for a neuromorphic compiler to talk to. And then, as Brian said earlier, this could then be targeted by existing libraries and intermediate representations like NIR. And this means that people can kind of interact with this at multiple levels. So users don't really care what's beneath this whole thing. They could pick a VM of some existing neuromorphic system and point their whatever spiky neural network library they want at it and simulate their model on it. They'd be really happy. Compiler developers have some way they can test their compiler on lots of different platforms, which is cool. System on chip designers can start like combining cores and bits of memory and interconnect and stuff into systems. And these, if they make it in this representation, then they can actually run stuff on it. So it's not just, they don't have to also do that work. and people who are designing hardware can like plug their hardware into this library. So I think this kind of vision might make sense for like a way forward for a virtual machine ecosystem. And the caveats on this, I did one course on system on chip design. I don't really know what I'm talking about. I talked about System C mostly because it's the only tool I've used, but I think this argument applies to any kind of open source system level modeling tool. I think it makes sense to use industry standards. It seems silly not to, really. And finally, as an academic, we always try and self-promote a little bit. So if anyone's interested in these ideas, we've got PhD funding available at Sussex, and I'd love to supervise projects in this area. So please contact me on the details on the front of the slides. Thank you very much.
Awesome. Thank you, Jamie. I'll wait a moment to see if anybody has any questions, or I wonder if I'm even seeing the right communal chat here. But that was a really nice disaggregation of what Project Phasor might pan out to be. And it does make things really a lot more clear. So there are certain parts of that pyramid that I suppose only the hardware vendors could develop, I guess because of proprietary information, et cetera, about their chip. So who do you think is the, and this isn't necessarily directed to you, Jamie, it would be great to have everybody chime in. But yeah, who do you think would be the best fit for different tasks across that stack?
I mean, I think the nice thing with the behavioral model is you don't necessarily need to leak any super secret stuff, right? Like, if you want anyone to use your chip, then in my opinion, you like Intel ships massive, or at least used to ship massive manuals for their CPUs, which told you what all the registers did, right? Like that information should be available. There's no reason that information shouldn't be available for commercial neuromorphic chips. Like, the fact it's not is a problem, but I don't think that should necessarily be the case.
I think some folk would disagree with that just because money talks, right? They don't want to keep their low-level details secret. But yeah,
it's security through obscurity, right? It doesn't really help anyone. And I think that's that's the kind of thing open initiatives like this should push against, I think.
Mm-hmm.
I completely agree with Jamie here, if I can chime in. If you're producing something that needs to be used by somebody else, it needs to have a public interface, a well-documented interface. And part of that, in my opinion, is providing an accurate simulation of the hardware. And we have simulations of our chips that you can use and deploy to, in fact, to test out and debug, because it just makes it so much easier. Debugging on hardware is a pain. Debugging in simulation is so much easier. And yeah, this stuff should be well documented, in my opinion.
And yeah, I suppose that even within that realm, there are various abstractions of simulations that you can achieve. Do we need cycle accurate simulations? Probably no. I don't know. But we don't have to go so low level to the point where companies that do treat their chips super sensitively need to even leak that kind of information. So it does seem like there is a big scope for academics that, I guess, that don't know what the layout of your buffer looks like. It can still kind of contribute here.
That's kind of my opinion. I don't really, like Dylan says, like behavioral level, the information you need to make a behavioral level simulation, that should be on your data sheet, right? Like that shouldn't be secret. Like the implementation, sure, no one's saying that commercial companies should share the Verilog or whatever, the layout, but like the behavior is the specification of the thing that you're trying to sell to people. Like, yeah.
Mm-hmm. Cool. So with that, thanks a lot, Jamie. I think we can keep moving forward. I'll let you decide, Brian. So we've got Florence or William or whoever that is up for it.
Okay, is William here?
Hey, how y'all doing?
Okay, yeah, let's hand it over to William, because I don't know if he has to drop off early.
Yeah, no worries. Sorry, I'm at check-in at the airport, but it's nice to chat with you all. Thanks for inviting me, Brian. So I am the founder of what we'd say is kind of an analogous org or setup to what you all are doing. So it's a nonprofit called the Unitary Foundation, and we are a public goods and open source nonprofit for quantum technologies. So quantum sensing, quantum networks, quantum computing, where there is, well, a lot to build. And a lot of what's been discussed on this call, we run into, there are things that academia is good at doing, which is making new papers. And there are things that can be VC funded, but there's all this other stuff in the middle, particularly around open source software architecture, standards, benchmarking, educational materials, professional networks, all that kind of stuff that is very important for a new space, but isn't easy to get funded. So I can tell you a little bit about how we set things up at Unitary Foundation. I think some of you know already, but and a little bit about what we've learned there. So Unitary Foundation does three main things today. The first is we run a microgrant program, which is what we started with. We secondly also have an internal technical team we call our labs team, and they work on larger public goods projects. There's about 12 people in that team right now. The projects we've chosen to focus on are benchmarking and compilation. And so we have open source software and other platforms and things in those spaces that we build and maintain. And the third thing that we do is different sets of community work. So we have a Discord, we run the major developer survey in the space every year. We run bounty-based hackathons and other events and other kinds of grab bag community things. So and I can dive into each of those in a moment, but one thing that any new organization like you all is, I'm sure, asking is, how is this funded? How do you get set up? All that kind of thing. So let me tell you how we got started. So we got started with the microgrant program. And actually it was like a very low activation energy. This was about 6 years ago. I just put out a blog. So I'd worked on, so I'd led the release of really some of the first open source quantum computing programming stacks. And when we open sourced them, we thought it would be, the usual suspects working on quantum computing, academics from, I don't know, Caltech, Harvard, wherever. But just by putting it online and not by doing that much marketing, we started to get good pull requests from unexpected places, like software engineers in Eastern Europe or a high school student in Ireland. And that got me thinking that maybe this was more accessible and less esoteric than you might think, which is true. And so I started this microgrant program by putting out a blog post and saying, I'll give out 3 grants of $2,000 each. And then some other people jumped in and said, here's another 6,000, here's a little more, do a little more. We gave out 5 or 6 grants. That traction meant I could start going to some other companies in the space and saying, do you want to just put in, gosh, like I had several phone calls with Microsoft over the course of the first 2 months, and they were like, okay, we'll give you $2,000. It's like, gosh, was it worth it? You could have just not had the phone calls and saved me that time. But then I got to say they pitched in a bit, and it sort of snowballed from there. So for the first year, we gave out, I can't remember, maybe 14 microgrants, and then I took a little bit of time to apply for our first research grant of funding. And so we're funded in 2 ways today. So we have donations, kind of like that original microgrant program, but it's structured as like a corporate member model, sort of like how the Linux Foundation does it. We've got 2 tiers, a 25K tier and a 100K tier. Also, some people give a little bit less. So that funds, I don't know, maybe 30 to 40% of our annual budget. The most significant funding, which funds our staff, are research grants from the NSF, from the DOE, from the European Union. And so I'll say, let me say 2 kind of synthetic takeaways from that path. One is doing something that doesn't require very much money, but can build traction very quickly, just so you're getting going, helps a lot. Because then, I don't know of any other organization in neuromorphic computing like you guys. You'll be the first ones. If you start doing the first thing, people will start to recognize you, even if you don't have to put that much money down and do big, complicated programs. just what's something small you can do that shows and proves you exist to then get to the next milestone of funding. So that's one recommendation. And the second one is that you can compete for these grants with national labs and academia. A lot of these projects, academia is not that well situated to do. If they are, they should be getting the funding, not you. If it's come up with a new idea and write a paper, great. But if it's making a compiler architecture, it's really hard in academia to have something that's maintained and interfaces and has good UI, like all that kind of stuff. Whereas you guys can actually hire software engineers and you'll be a lot lower overhead than any national lab. I mean, you know what those overhead rates are, they're crazy. So because you're in an exciting and important and new space, don't talk yourselves out of applying for grants from some of the larger research orgs and institutions. So those would be my two summary things. I can talk a lot more if you've got questions, but that's sort of a quick overview about us, and it's really exciting to see more people think about this kind of model. It's been pretty important in our space. And secondly, I run a Unitary Fund, but what actually pays me is being an investor. So I do early stage investments in stuff, and I've been looking at neuromorphic computing too. So it's nice to to get to meet a lot of you as well. We haven't written a check there yet, but that's great. So yeah, maybe I'll direct to Q&A. Is there anything else I can answer for you guys? What would be helpful?
Awesome, thank you, William. I'll open up questions. I think even the hosts, Brian, etc. If you have any questions, feel free to shoot them William's way.
I just want to say thanks for joining. I'm glad you took time out of your travel, because we had a small group on this and came up mostly blank, and I feel like you gave us a really good template to start with.
So one thing that sounds pretty decent to me, I mean, coming from academia where we're hyper optimized for papers and it is difficult to maintain long-term sustainable open source projects. I mean, granted, we do try. But it feels like Project Phasor is in this really nice sweet spot that has this industry interest, but has a lot of ties to academia, where you could be incentivizing industry to make their work a little bit more open, a little bit more accessible to academics, such that they are able to contribute more meaningfully in that kind of, I guess, maybe it is long-term, maybe it isn't, but at the very least, Project Phasor could be the ones that hire those software devs that are not just gunning for the next NeuroAI spotlight paper, and it could be something that the rest of the community work with. So this is, really cool stuff. I think with that, go on.
I mean, if you want, I could, so if just sort of, I mean, you know your space better than I do, but let me say that this benchmarking area has been a perennial thing we've been focused on, and it's been a really big public goods problem. So, and it matters for everybody. I mean, I think in quantum technology, in quantum computing, and also for neuromorphic, people from the outside, investors and users, are saying, show me the benchmarks that this is better, and or at least it's better than something else, or at least it's getting better over time. And you probably have a situation where there's not standard benchmarks, and people all are doing different benchmarks of different kinds of hardware. Is that the case, or are there relatively standardized ones?
So I think algorithmically, Jason Yik, a PhD from Harvard, he has done a really good job with Neurobench in aiming to standardize these things, and he's also done a really good job in making it extendable. So I know if he was, I think he's listening in on the call, but yeah, if he had a voice, he would say, hey, it's there. Now we just need industry to provide industry relevant benchmarks if they don't already exist. So there is some infrastructure there that can be extended with the right investments.
That's great. It's great that you've got that start, and like that project to work well, it needs to, there's a lot of non-academic, sort of non-novel work that needs to happen, right? You need to integrate it with new hardware backends, you need to keep it up to date, you need to maintain it, you want the software to, benchmark efficiently. so it's something that academia has trouble with because running an old benchmark is not new, and it's not a company. So if maybe this NeuroBench project is it, but if you can start adopting long-term maintenance support and running, and then providing openly the benchmarks from that, then that could be an impactful way to get started.
Yeah, absolutely. And even interfacing it with the one thing in the chat about compiler first and building better simulators of the system C abstraction, it could be the case that these benchmarks are not necessarily run on hardware, but you're able to do what much of the architecture community do, and that is get emulations of neuromorphic accelerators that don't exist yet, but that is somewhere that Project Phasor could sit in guiding us on what hardware could be optimized to a particular set of benchmarks as well.
Cool.
It also sounds
great
like
to meet you.
Sorry to jump in. It also sounds like this, in order to have this continuous upgrade of a benchmark and updating and inclusion of new results and review of new results, you also need some sort of funding to be able to maintain this, and some sort of governance body to be able to make decisions of malpractice or updated standards or whatever else that needs doing. So it's possible that also Project Phasor can be used as this kind of a body. So that's nice.
Awesome. All right. So with that, yeah, thanks so much for your time, William. I don't know if you're flying out.
All right,
or
everybody.
flying.
Yeah, I'm gonna hop in the security line. Take care and feel free to reach out if you've got other questions. Bye.
Awesome. All right. Have fun with that. Great. So I think we can keep moving forward. Is it Florence up next?
Can you talk a little bit about compilers, and
Sure.
then Florence. So Jamie already touched on this a bit, but I think the goal of Project Phasor is to be more protocols and not platforms. And the protocol we could start with is Muir. It's already a high-level graph that's supported by many neuromorphic frameworks, and so you can describe it in one framework and compile it with whatever compiler we come up with theoretically, which would have some nice properties. And then when we talk about compilers, Jamie brought this up earlier on. It's important to differentiate between the type of compiler that's doing the partitioning of your graph and allocating it to different parts of your hardware, versus I think what people usually think of as a compiler, where you're compiling down to the assembly machine code. And a lot of neuromorphic hardware just has fixed function neurons, or you have to roll your own assembly or rely on existing microcode programs that are provided by the vendor. And I think it would be nice to have a virtual machine that does actually do the compiling as you normally think of it. And that's what's done in conventional machine learning compilers like OpenXLA or Triton. And in those cases, they have to worry about a lot of different constraints around things like fusion and rematerialization. This is not this is something I've heard about all the time with compiler folks on my team at Google, but didn't really hear about on the neuromorphic world until Seneca paper came out like last year or something. And they did they called it depth first evaluation of the network. That saves you from having to write back out to memory. And I think I would like us as a community to be more open-minded about what we call neuromorphic hardware. Consider hardware that has a cache hierarchy, especially when you're looking at really, really large models, and the weights that are active for any given duration might just be a small fraction. You can think of something like a mixture of experts, but more like the a mixture of 1 million experts that I think someone presented on at Google from Google at Telluride. I didn't get to talk to him, but I think a bunch of you guys did. I think that is a really neat workload that I think we could really help support people research toward. And that would actually map really well to a cache hierarchy, in which case potentially things like fusion and rematerialization become much more important. And so in that case, I'm wondering if we can rely or lean on MLIR or existing compilers to do a lot of the heavy lifting, but I'm not a compiler expert. And yes, Patriots.
Nope, that was a fat finger. I'm sorry, I didn't mean to press that button.
Right. So, any questions on the compiler? I don't have much in the way of like potential answers, but I feel like we need to find a good compiler expert.
Yeah, I think that is probably the next most important thing, pulling in the compiler experts and the neuromorphic community into this conversation. So you know who you are. Reach out to Brian when you're ready to. In the interest of time, let's keep pushing forward. Yeah.
Yeah, I can talk a bit more next, and Dylan, though, please feel free to jump in with more neuromorphic focused thoughts on heterogeneous integration. So one of the thinking, and Dylan and Jamie mentioned this earlier, of integrating neuromorphic processors into existing stacks, that thinking of it, is it going to be the processor for primary applications? Probably not. CPUs and GPUs, as Brian said, are good at what they do. So if we're thinking about neuromorphic processors coexisting with standard von Neumann architectures, we think about it as a coprocessor that can then integrate into existing applications that benefit from neuromorphics, things that are real time, things that are low power. My background a lot is in edge computing, so I think a lot about like, what are the software pieces of software infrastructure that I would want that would encourage me as a user to pick up a neuromorphic processor and integrate it into my stack of hardware, integrate it into my application for, let's say, robotics. I'll do a lot of robotics, or I'll do a lot of wearables, these applications that are real-time and low power and have latency constraints. So you can use, there's a lot of edge coprocessors like FPGAs, and Google has the Coral the TPUs that run off Coral. And then there's a bunch of different like neural processing units, like Jamie was mentioning, the proprietary vendors who will make their little proprietary chips that accelerate neuromorphic application, neural network applications. If we want to do that for neuromorphics, we want to have the same sort of ecosystem of software like Vitis and OpenVINO for Xilinx and Intel FPGAs, or Onyx and Glow as sort of like frameworks for being able to load these models in the hardware. But even then, we still have a lot of what Brian likes to talk about as software glue in order to make, just like, how do we load data into FPGAs efficiently? How do we schedule everything so that we're using our hardware optimally? And like, the thing that I like to think of as the type of software that we could build is sort of like Xilinx's Pedersen, which takes care of a lot, which is a system for making drivers for Xilinx FPGAs, where they, because they know about their hardware, write all the glue code for you. I imagine something for neuromorphic applications being something that would be really useful, as Dylan brought up, that a non-commercial, non-academic entity could contribute a lot to, given that it's not hardware specific. We want to make something that's a very abstract layer of letting people be creative with the low-level stuff while we take care of all the glue code.
Very cool. And Dylan, did you want to chime in here? I know this is the.
Please chime in.
Yeah, just wanted to say this is something which we also consider very important. We see a lot of our chips as being elements of a hardware system that will have to integrate with a system processor. Using standards is a good way to integrate here. So we try and adopt standard interfacing for our chips, something which would just make our processor look like a peripheral. I think promoting standards in the other way is also useful. So if there's a neuromorphic standard that can be pushed towards industry that's adopted by multiple companies, this is another way to make sure that it's easy to pick up and use neuromorphic hardware, easy for a designer, a hardware designer, a hardware engineer to pick up and use neuromorphic processors and coprocessors. And there's something that Project Phasor is well placed to mediate between.
Okay. And yeah, I'm still on the topic of heterogeneous integration. Thinking about it more broadly, some other things I'm interested in is combining digital and analog neuromorphic computing. And analog is something that I'm not very familiar with, and so to me it's like a bit magical and something I want to understand better. But I feel like there's a lot that could happen there if we have virtual machines for all these different types of neuromorphic hardware, and we can use each type to their given strengths. I would like people to do research more in that direction. I feel like there's a lot of work already with things like analog in the loop being shown to be able to train analog hardware to do something useful. It's just, I feel like it's such a rich place to explore, and the VMs could really enable a lot of that exploration. And I've talked about this with some folks. Can analog be useful in the data center, where manufacturing variance is an issue, and it's not just a variance that's easily averaged out, but it's like a bias. But could that actually be useful at a large scale potentially for reinforcement learning or generative AI, where some randomness is beneficial? And if in the cloud you're operating with these, like, let's say you have 1 million analog chips doing reinforcement learning, Monte Carlo search. If you sample them intelligently, does that average out the bias or anything like that? Just stuff like that, I feel like would be really fun to enable people to experiment with.
Yeah,
I'll stop there.
And to tie that back into some of the points that were brought up earlier, I mean, it could be a matter of having folk like Unitary contribute relevant benchmarks that really do showcase the benefit of analog. I'm always hesitant on limiting it to analog, because of course there's a lot of people in the neuromorphic community that just keep going deeper and deeper into the stack. Got the material science and device communities that are also making these neuromorphic devices. Though given that the Project Phasor really does seem to be this, I don't want to call it an interface, but it can be that. It can be an interface to industry and large-scale chips that are solving immediate deep learning-esque or cognitive type problems. It does seem like those deeper in the stack advances are perhaps a longer-term horizon at the moment. Is that fair to say? I of course don't want to be ostracizing the neuromorphic community here, but clarity would be good.
I mean, to me, analog is a big question mark in this, right? It doesn't fit so nicely into our kind of neuromorphic is just another sort of system on chip. We can make a virtual machine type thing. But if you're thinking about funding, I mean, at least in the UK, the device people at the forefront are the ones that have got the government's ear on neuromorphic funding. It's all memorous to people and exotic device folk. They might be missing a trick.
I feel like a lot of this is also, it's a matter of the hierarchy at which you want to do benchmarking. If you want to do benchmark of a particular circuit that does something very specialized versus if you want to do an application level benchmarking, which is roughly what NeuroBench is. I mean, not roughly, the NeuroBench is at an application level. So you have to solve an entire problem and then show how you've done it at the system level. Analog is a part of that. It's not maybe the whole story, and that's important to acknowledge. Yes, even to the question on screen, does analog have something to, or the previous slide, does analog have something to do with data centers? Probably, if you think at the right hierarchy, and if you set up the right benchmarks and think of the entire system, the entire data center, maybe not necessarily analog at the data center scale, like a Cerebrus, but fully analog, but with smaller components that are analog and some are digital. I did have one question though, and in this quest where maybe you could do, let's say, architecture exploration or some sort of algorithmic exploration where you want to put to associate some numbers, some KPIs with the performance. Sometimes, at least at the edge, you really want to say something about the power consumption of the system that you have, and I feel like, do you have any thoughts about how this could be addressed? Because doing power estimations and creating simulators that are relatively accurate for power is fun.
I think some people have to leave at the hour, but really quick, yeah, the sim power is going to be really important, and I'm really excited to figure out how to do that accurately, or even if not accurately, relatively, comparing algorithms on a given hardware at least. But yeah, I don't have any good answers except that yes, it's important.
Which is perfectly okay. I think this is the right time for questions so that we know who needs to be doing what, right? Awesome. I think that we can start to wrap up. Are there any closing remarks from anyone on your side?
Well,
Okay.
I can't. Yeah, one more.
Yes.
Hi. Okay. Before I start, I just want to say I have been so richly blessed with the amount of knowledge pouring out from every speaker and contributions and the questions that have been answered so far. Now that we've spoken about the algorithms, the hardwares, what we're trying to do, and reflecting back to what William said on benchmarking and creating a benchmark, I'm a PhD student, okay? And what we're doing right now is, instead of focusing on just bringing out papers, we're trying to bring out papers at the same time commercialize what we're doing, in the sense that not everybody that finishes from the PhD program wants to remain in academia. They want to go into industry. And before you go into industry, what you're working on, what you've devoted a number of years in your life to do, is it used for real life problems? So I am basically working on using neuromorphic data for real life applications, like multi-class classifications, detections, the general, how do we use NeuroAI for real life problems? And that brought me back to, you cannot see the efficiency of spiking neural networks on spiking hardware if you're not working with the right data sets. So I would be speaking on what kind of data would we be able to use for spiking neural nets on neuromorphic hardware, and how can we maximize? How can we say, okay, I know there are traditional models that already exist. I know they've done, models to do disease classifications, medical imaging, or autonomous driving, and then here we are in NeuroAI saying, hi, we have something better that costs less and is faster, but we've not been able to do the real life problems yet. In a way, we will get there. And that brings me back to the data. What kind of data do we have? Brian, I do not have control of the slide, so you can go to the next one. Now, I did a mini survey where I was like, okay, there are a whole bunch of data out there, and this is an estimated pie chart that shows the percentage of data we have in the world right now. I kind of did a mini like scrap from Kaggle, from Google. I was like, okay, just give me a rough estimate of what kind of data do we have out there, RGB data in particular, computer vision data. And then we have this percentage right here. You see the one for augmented reality, image segmentation, facial recognition, object detection. See how big they are? And go to the next one. Just see the next slide, please. You see just how many percentage of that is event data. See that? We just have 4.1. And in order to maximize the effect of SNNs, we need to feed it data that it can understand. And what we know about event-based data, that's event data gotten from event cameras, is that they are spikes in a way. They can, let me not go deep. Event data, event camera can capture the difference in pixel intensity, right? All through your data, and then they generate spikes from that. So one way we can maximize the effect of spiking neural networks or neuromorphic hardware is if we actually feed it the right data. But we have this really big gap of not having enough right data out there for our models. Now, I'm going to speak from a personal perspective when I say I started spiking neural networks roughly a year ago. I've been really neck deep into it roughly a year ago. And then I noticed that most of this data set are not public. And even when you read the papers of what they've achieved, what they've done, I'm like, wow, this is so amazing. And then you send emails like, hi, this is what you've done. I like it, and I want to build on it. Definitely, as a research community is supposed to be, you send the mail and can you make your data set public? It's like there's this closed lid on data set, knowing fully well that we're all trying to, show the world that neuromorphic computing is cheaper, less cost intensive, and we're trying to maximize the hardware. Okay, so the feedback is really poor. And I feel like coming from a user perspective, as well as, we should be user focused, as well as model perspective, we should find a way in this project to create an open source data warehouse for neuromorphic data. I went through, I think we have the one for Tonic. Dr. Jason did the SNN touch, and he gave us how to onboard data set on Tonic onto our platform, because I use SNN touch as like the backbone of my research, sometimes back in Jelly. And most of the time I realized that I've been running on simulators. I do V2E simulators where I'm converting RGB frames frame by frame before I can, get spikes, like generate events from RGB. And that in itself is another work to be done before I then onboard these data into my model before I try to get on the hardware. So you see the whole step-by-step process. It's like dampening the progress that can potentially happen. So if we have a public warehouse for neuromorphic data that can be onboarded onto neuromorphic softwares, algorithms that can then be used on neuromorphic hardware, I believe we can see the maximum potential of neuromorphic hardware in general. So it's like a chain reaction. Give me the right data so I can get on the right algorithm so I can use on the right hardware in terms. So I am speaking from a user perspective. Oh yeah, and then the benefits of NeuroAI, having event data in particular on neuromorphic computing is you get reduced redundancy and bandwidth. You have the spatial-temporal efficiency, and then event cameras have a way of providing real-time processing. So as you're noticing the changes in the event as it's happening, you're recording it, right? And then these are the simulators I've used so far. I believe Nest is good for large neuromorphic models. I also use Nengo GUI, but it's not really big on large data sets. So I'm going to go with Next for those that want to onboard on that. And the V2E simulator is good. You just have to fine tune the parameters to get it to work well, know when to end your timestamps, know when to increase your frequency or reduce your frequency. Yeah, and that's the link to the data set. Any questions? I really know it spoke. Any questions? None?
That was a really nice talk. Thank you. So I think this is a big problem, right? It's a sort of chicken and egg situation that we need more neuromorphic data sets.
Yes.
Scale.
And that's why I did the spreadsheet.
Yeah. And if you have to convert RGB data, then it's not really, you're already at a disadvantage as a neuromorphic application. But because there's no large scale neuromorphic processing, there's not many large-scale neuromorphic data sets.
Exactly. What we're currently doing in the lab right now, because we got the Dosan robotic arm, we got the event camera, we got the rotating lenses, we're trying to actually create our own data set after seeing what is out there, because it's kind of difficult to get like data set, because we got the open neuromorphic fall detection and object classification. We got all the data set, and we're trying to like create our own data set, because most of the papers I read, they did their own merging of different data sets. But we're not trying to do that. We're trying to simulate an environment where we can create neuromorphic data sets that we can use on neuromorphic hardware. Because
and I think that could be a target for microfunding, right? Like, it's a kind of project that like students could do with a small amount of money in a few months, right? It's like make some kind of interesting data set for it, relevant to some application.
Yeah, we had a good breakthrough, I think, 2 weeks ago, because we got a chessboard and we're trying to like detect the change, like generate events from putting the chessboard on in front of the event camera and with the rotating lens, and see if we can generate event for that. And we got very good results for that. But the summary is, we can't be here saying neuromorphic computing is amazing. Meanwhile, we don't have a benchmark to compare with already existing traditional models.
It's a similar issue as for the benchmarks.
Yes.
It's probably good, as William was saying, and it's difficult for anybody to want to invest in it. So on the academic side, it sort of takes away from your research time. On the commercial side, it's just very expensive and time consuming to do this stuff. So I think the micro funding approach for producing data sets as well as benchmarks is a great idea.
Yeah. Okay. Any other questions?
I feel like in terms of less of a comment, just building on top of what Dylan was saying, that it's a chicken and egg problem, but also with if we're talking specifically about a DVS, then think of all of the DVSs in the world versus all of the RGB cameras in the world, and obviously you're going to have much more data and many more data sets that involve RGB than with DVS, coupled with the fact that it's not necessarily an industry standard. What does AER mean to someone who is outside of the community? So it's coupled with a lot of different things. There's the lack of commercial traction because they've found a way, and it's a way that works, and they would change it to some extent. And so I think what with other efforts with like NeuroBench and Edge AI or TinyML Foundation, what we're trying to do is bring the pain to the data sets that as the industry currently uses them. So yes, neuromorphics is good. Neuromorphics should be better for spiking data, but there has to be a way to convince people, probably on applications and with data that already exist, to show them that you can also beat them at their own game, at least with some data modalities.
And at least at the edge, no one is going to make a spiking IMU, right? Like, IMU is always going to be probably either analog or digital, and you've got to deal with that. Like, it's different. Like, I think vision is maybe a specific thing, maybe audio, but I think, as you say, a lot of like edge sensing is going to remain an edge sensor.
Maybe it's also just a matter of scale, proving that neuromorphics can work at certain scales, and then building up that market share, let's say, of or the idea seeded in more people's minds that neuromorphics is a thing, and you can do how it works, and at the intuition level. That would also bring a bit more pressure to invest more into DVSs and into larger sensors.
I do believe that if we can find an applicable methodology of, say, we create like a really nice model, and we outline how, because that is what I'm aiming for my research. I'm looking at commercializing what I'm creating right now when I'm done gathering the data, and then showing that, oh, it does this, and I'm doing spiking neural networks and medical imagery, so it does this, and then it does this at a cheaper cost and less computational intense, and then it does this better than what you already have, and they're using it. So if we have that one breakthrough, it could work, basically. But the problem we have currently is there is no spiking data out there that is just large enough to hit right. We just have to do the whole conversion. Like I've been doing a whole lot of RGB. I use the V2E simulator to do conversion from vision frame by frame. And that in itself is very exhausting. But I will survive. We will survive. So if we can actually add this into one of the goals for Project Phasor, where we're like trying, different labs are like collaborating, people are responding to emails about their research and, you know, releasing their data out there for people to work with and grow with. It would be nice because there are a few papers I've read so far that have had, you know, good progress on spiking neural networks, neuromorphic computing, and what they've been able to achieve with it, but they're not really public with their data sets, which is a thing. I believe Brian is used to me ranting like this when it comes to I know he's
a lot of good things come up.
who's used to it, but it's just sad. Okay, thank you very much. And that's it.
Yes, thank you, Pedersen.
Mm.
Okay, so just to wrap up the meeting, Jason had to log off at 11, but we'll keep going for a little bit. A little bit on strategy and governance going forward. I had a post yesterday about this, but for the strategy of the next month, I feel like we should concentrate on trying to convince neuromorphic users, folks like Mercedes, Prophecy, the academic community, that, you know, this is something that would bring value to them as a user first kind of effort. We're trying to really make things easy to use for researchers, and then hopefully take that and convince more producers to get on board. I don't think we've explicitly said it, but Dylan is from SynSense, and they've offered their software stack as a way to bootstrap the effort, which is awesome. But it'll be really important to get other folks on board who are thinking similarly to SynSense, and figure out how they'll hammer things out. And then going forward, hopefully we'll make it easier for new players to enter and contribute. Hopefully we'll reduce the amount of effort it takes to get involved in the community. And finally, you know, there's a greater enemy here, which is NVIDIA and the rest of machine learning accelerators. And you know, I think if we don't get this right, you know, quickly, when things turn around, you know, people are going to be able to follow fast, and, you know, I think take what is rightly belonging to the community here, who's invested so much time and effort into it. I would hate for NVIDIA to swoop in and just pour a bunch of money to make something neuromorphic and win out in the end. But yeah, I'm hoping that, you know, everyone's willing to work together to, you know, make that finish line closer. So, oh, and yeah, the last one is governance options. I don't know much about each of these. My experiences so far with ML Commons, and I feel like that's a good one. David Cantor was open to housing a compiler effort like this within it, and he's the head of all of ML Commons. I know the NeuroAI Foundation, which Pedersen is a part of. I think he's actually chairing a neuromorphic working group within NeuroAI Foundation. They're also interested in housing something like this there. Pedersen, I don't know if you want to speak on the TinyML NeuroAI Foundation a bit since you're here. Maybe he dropped out. Okay. But yeah, there's other options. I feel like as a community, we should really consider the pros and cons of each and figure out where a good home is for something like this. Yeah. We're 15 over. I feel like we should probably just, if there's any more discussion, we should give people time to watch the recording and maybe try to schedule another meeting where people are prepared with their ideas and have more of a discussion. If anybody has anything else. Cool. Yeah. It's been awesome working with you guys, and it's great to see people excited about the ideas here. So thanks for joining, everybody.
Bye, guys. Thank you.
Thanks, everyone. Bye.